to everyone and welcome to our first seminar series for spring 2021. And we are privileged to have our guest speaker who, proud to join in OSU, worked as a senior R&D scientist at Utopia Compression Corporation, where he led a number of research projects on unmanned aerial systems, detect and avoid target tracking and target handoff in GPS-denied environments. Presently, he's an assistant professor in the School of Mechanical and Aerospace Engineering, where his research interests include distributed optimization and learning, nonlinear control and estimation, and multi-agent systems. Please help me welcome Dr. He Bai.
All right, thank you very much. Thank you for the introduction. It's really my honor to present to colleagues here about some of my recent research on optimization and learning. I just learned this is the first seminar this semester, so hopefully I give a good start and you'll get better and better presenters and seminars over time. So, all right, so let me get started. If you don't mind, I'm gonna close this window. So, okay, so I assume everybody hears me okay and see my screen?
Yes, I can see your screen, Dr. Bai.
Okay, cool. All right, so this is, I'm gonna talk briefly about some of my recent research on decentralized Bayesian learning. This is some work funded by NSF and also Army. Recently, we look at problems like in the machine learning community with decentralized data. How do we do training and learning in decentralized scenario? So before, sorry, how could I? Okay, so before I start, I'd like to just give a brief, sorry, what happened? Give a very brief introduction about myself. So I had my PhD from Rensselaer Polytechnic Institute in Troy, New York, and then 1 year postdoc at Northwestern. There I was mainly doing nonlinear control for multi-agent systems and using dynamical system properties to control multiple robotic arms for coordinated motions, satellites for interferometry motions, and some other multi-agent, multi-robotic tasks. And then I moved to industry, spent 5 years there. Mainly, I work on detect and avoid problems. So this is integrating of unmanned aerial system into the national airspace. One of the challenges to how to detect another aircraft without a human sitting on board, using machine vision, and how to track it over time, and then eventually make a decision to maneuver or not to maneuver automatically. So that's kind of one of the main project we've worked on, funded through DARPA Air Force, to do a vision-based target detection, tracking, and in terms of also ranging to the intruder using just camera sensors. And then I joined the OSU in 2015 and had some small project, but this is a recent project we got from NSF. This is a team of faculties from our department and also Dr. Vance from Aviation Education. So here we want to look at small UAVs operating at low altitude space because there's a lot of turbulent effect. How do we handle that through better controls and better estimation techniques, and how does that eventually impact pilot operations? Like how does that impact human operations on aircrafts, particularly small aircraft? So we're trying to look at a closed loop performance from wind sensing all the way to wind prediction, and then eventually provide information to remote pilot in terms to help its decision-making and support its operations in low altitude airspace. They just started the project, I think in 2020, just 1 year after that. Made some progress, so certainly we'll be happy to talk about this a little bit towards the end of this presentation. So the outline of this talk will have two parts. I'll spend kind of roughly 30 minutes on the decentralized learning problem recently we looked at and present you some results. And then I also want to take this opportunity to talk a little bit about some human-vehicle interaction problems we're looking at. I understand there's a lot of expertise within IEM, and so which I like to hear your thoughts. So really these two topics, I think the first one is more or less relevant to optimization, which is one strength area in IEM, and the other one is kind of human in the loop, human decision making. That's another kind of focus area in IEM. So hopefully we could have some synergistic discussions and potential collaboration opportunities on both of these topics. So I'll start with the kind of the first topic on the learning. So most of you know, like the machine learning now is a very hot topic because a lot of data are coming in. How do you process the data? And the future operations really will consist of additional kind of aspect in terms of highly connected systems. These could be systems coming from IoT, smart devices, or swarm robots. These systems going to produce a lot of data and different data sources. How do you fuse them to extract information from all of these connected devices? So there's a lot of data collection, processing, and analytics tools needed, particularly to get data-driven insights and also decision-making and the prediction capabilities for based on big data. So if you look at it from a centralized point of view, which means you're going to send all the data from these connected devices to a central location for processing, and then send back the process result to individual locations for actions, then it has a lot of challenges. One is communication, right? You need to send a lot of data. Second is privacy, security issue. When you send the raw data, you have the potential of posing the data to the internet, and then privacy may be damaged, right? So and also there's single point failure because the centralized processing unit, if that has a problem, then really all of the data is no use. So that's kind of the process and the thought process that we had. If we have a centralized learning node, then it has all of this shortcomings in terms of communication, privacy, and single point failure. So this is a typical process of how a typical machine learning process. You get the training data, you optimize you optimize the data, essentially the learning, and then you get your model. So the model with the learned parameters, this could be like neural networks weights. And after that, you use your trained model to infer or to predict what's going to happen given additional input data. So in terms of the learning architecture, I explained the centralized learning has all of its drawbacks. So this is kind of a picture of the centralized learning. Everything is sent to a main computing server. On the other end of the architecture, there's a decentralized one where everyone has some computational capabilities, and through communication, these arrows denotes communication. They try to recover the optimal parameters by sharing information between them. So between these computing nodes, so they don't need a centralized computing server. They can do their local processing, and then they share some parameters of their model. They don't directly share data. They don't directly share their training data. They only share parameters of their model. So that's the decentralized version we're going to look at. Also inside the machine learning community, there's two other kind of architecture. One is called federated learning. The other one is called distributed. So the distributed learning is more focused on the computational aspect. For example, if you have a multi-core processor, how do you distribute the computation into the cores and then use that to speed up the training or speed up the computation. The federated is also similar, but it's looking at something similar to this process where you have a central node that aggregate information from the individual data or individual agent, and then once the information is aggregated, it sends back the updated parameters. So these three kind of architectures all require some sort of central node, either to process the data or to aggregate the data or to aggregate information. So what we're looking at is sort of a decentralized version where we don't have a central node or a central processing unit. So here's another picture kind of showing the differences. One is the centralized. So in the centralized case, essentially all of the data from individual agent, they're pulled together to the central unit. So that at the central unit, you have input, all kinds of input, and you have all kinds of output. Then you train your neural network to detect whether these are duck or this is not duck. Whereas for a decentralized case, everybody will have different sets of data. Some of them will have these duck and not duck classes. Some of them will have different classes. And then they, through communications, they try to recover the same performance as if the data were aggregated at the central location. So really here, we're looking at communicating parameters or estimates between agents such that the agent will recover the centralized performance or the centralized trained model. So just a little bit on the communication network. Probably this, you're already familiar with this, but basically we use a graph to represent the nodes or the agents. So the graph, they are undirected graph, they are connected. And whenever there's a link, that means these two agents can talk to each other. And to facilitate the analysis, we define all kinds of matrices, adjacency matrix, degree matrix, incidence matrix. But eventually, we rely on this Laplacian matrix, which is called L here. It's basically does this aggregation of differences. So if you have the ith row of this L matrix multiply a vector, really what this says is I'm going to take the agent the xi and take xj, take the difference and sum them up. And what kind of xj I'm going to take? It's all coming from my neighboring set. For example, for agent 4, the neighboring set is 5, 7, 3, and 2. So I'm going to take x4 and take the difference between all of my neighbors and then aggregate them together as one number to be the aggregated difference. So the L times this vector of x will just give you that aggregated difference. Okay, so that's the key thing we use out of the graph structure. So basically, just undirected connected graph. Okay, so now let's move on to the problem of Bayes learning. So most of you might have used a neural network where they were trained based on stochastic gradient descent. That is basically it's a way of learning, but that's not Bayesian because it doesn't capture uncertainties involved in your parameters. So essentially, given a data, some training data, and also a model structure, which is your neural network model structure, all of those neural networks weights are unknown parameters you want to estimate. If you use like SGD to get the estimate, it's only a single point estimate, which doesn't have any kind of uncertainty measure. You don't know whether your training data is sufficient or not. You get an estimate. And that could potentially lead to overconfident predictions because you think your model is good, but maybe it's not. So of course, there's ways to kind of mitigate that issue, but one of them is to use Bayesian learning, where we're going to put prior distribution on the parameters and also using a likelihood coming from the data, the training data, and to get a posterior distribution. And once you get that distribution, you can measure its variance or entropy and to see how uncertain that estimate is. To give you idea whether your model is good enough or you need additional data to do the further training. So Bayesian learning really could quantify the uncertainty on the parameters, could also potentially avoid overfitting because you have an uncertainty measure and you know how large that is once you get your posterior. But that's in theory. So once you implement it for a real system, the exact solution to Bayes learning is intractable. So you can't really get the posterior distribution analytically, except in some very simple cases like Gaussian noise or some like a Kalman filter type of problems. So there are some approximate Bayesian learning tools. One is the one we're going to use here, talk about is MCMC, which is a Markov chain, Monte Carlo. And there's all the others. Variational Bayes has a lot of success recently in neural network, and also there's expectation propagation. But we're going to focus on MCMC at least in this talk. So the idea here is to do this decentralized learning problem. So let me make it a little bit more concrete. Let's say I have a network of n agents. So here the example, I have 5 agents. Okay, and then each of them have their own data set. I assume they're independent. So xi is the data set for agent I. And they have their own, I mean, here I assume they have the same model, so same neural network. And they are like parameters. Essentially the input and output, and also the parameter here, we're going to parameterize all of them with a distribution. So then the posterior, global posterior of the parameter or the model parameter, which are the weights in the neural network, is given by the following kind of formula. This is a Bayes formula. This is the posterior equals the prior times the not equals, proportional to the prior times the likelihood. And then there's a normalization constant, which is really the challenging part. It's very hard to compute that. So that's why this is a proportional sign here. And then given the prior here, the likelihood here, really we're decomposing that into n different copies. And inside each copy, we call this local posterior. That basically involves the likelihood for the individual agent's data. Okay, so this is the likelihood due to data xi. And then this is kind of a share of the prior for agent I. So I have 1 over n here. So essentially, this is not a posterior. I mean, we call it local posterior. So it's sort of a pseudo posterior. But basically, we call it local posterior just for simplification. So essentially, this is a multiplication of local posterior for all the agents. The idea here is, how do I reconstruct this global posterior based on only this local posterior information, because I don't have a central location to aggregate the data. The agent can only share their parameters W instead of sharing the data set X1, X2, and all the way to X5, right? So because the data set could be enormous, it's very large, so you don't want to share them. So how do we do that? So to do that, we draw on some early research on what they call Langevin dynamics, or on just the Langevin algorithm. Essentially, we write the global posterior as a energy function. So we write it as proportional to the exponential of some energy function that's taken from all the agents, okay? So if you recall, this is the local posterior. So we write the local posterior in terms of e to the ui omega, okay? And then the product here becomes the sum, because this is exponential. And then the ui is actually given by this formula. The ci is the constant that we cannot compute, but this guy we can compute. This is the local posterior. We have an explicit formula to compute that. So really the Langevin dynamics makes use of this energy function and drives this SDE, stochastic differential equation, with a Wiener process noise. So essentially here, this is a typical gradient flow. And then there's some additional noise with a specific variance square root of 2 here. So this is in continuous time, and it has been shown the distribution of W would converge to the P star W given certain conditions. I'll explain that a little bit. But this is in continuous time. And then to implement the algorithm, always we need to discretize it, so make it in terms of iterations. So this will be the iterative form of the Langevin dynamics. So again, it has a typical gradient descent part. So this part is the gradient part. And it also has a noise part. This V is actually a Gaussian noise with a specific covariance identity matrix. And the dW here is the size of your parameter space. Okay, so we can view this as a kind of a balance between exploration and exploitation. This part allows me to explore the energy function, which relates to my global posterior. And this part allows me to explore, because I don't want to always focus on the maximum value of the UI, which will correspond to the mode of the posterior. But I want to explore around it to get the actual distribution. So this noise effect actually allows me to explore around the mode and eventually converge to the actual posterior distribution. So the output of this are samples. So WK, these are at each point, these are samples of the posterior distribution. So after a certain burning period, or in our language, like after convergence, all of these samples WK will be a random, will be a draw from the posterior distribution. So this is the first order MCMC techniques. There has recently there has been a lot of interest in machine learning community because the typical way they were doing is to use this MH acceptance criteria, and then that takes a lot of time, and this one's supposed to scale better to higher dimensional data or higher dimensional parameters. So there's a lot of interest in analyzing Langevin dynamics in the past few years. What we did is, okay, so maybe I'll spend one more minute on the centralized one, and then I'll move to the decentralized one. So this one basically, as I said in here, we want the distribution because this is driven by noise. So the W here will have a kind of a equilibrium distribution or invariant distribution at the end. So we want that invariant distribution to converge to the P star, which is our target distribution. So essentially, people have shown that this convergence actually holds, which means the distribution of W coming from this Langevin dynamics will converge to the P star, which is the target posterior proportional to this functional form, if the P star satisfies a certain, they call it log Sobolev inequality, LSI. That inequality ensures this convergence always happens. And then actually the convergence in this case is exponential for the continuous time dynamics. Okay, and for the log Sobolev inequality, this is actually a generalization of log concave measures. Okay, log concave measures basically says all of these UIs has to be strongly convex, then that's log concave measures. But LSI, or this inequality, extends that, allows us to have perturbations. Okay, you can actually perturb, let's say this is a Gaussian function, but you can actually have bounded perturbations around the Gaussian distribution such that this black line, the distribution of this black line is still satisfying the LSI inequality. So there are also a lot of literature on what kind of measures actually satisfy LSI, the LSI inequality. So I just want to put this as an assumption. We're going to assume our target distribution P star here satisfies this LSI inequality given here. So now we move to the decentralized algorithm. So if you recall, the centralized algorithm is given by this. Really, the way to decentralize it is fairly simple. At least the way we're doing it is fairly simple. We're going to create two terms. This term is the interaction term. So the omega I minus omega j is the difference between agent I and agent j. And this aij is coming from the network architecture, which would be 1 if agent I can talk to agent j, and will be 0 if they cannot talk. So this one has the agent interaction part. And this one is the local data part. So if you look at the centralized version, it needs all the data to be aggregated so that you can take the gradient. But for this one, I only need my local data UI. So this is only coming from my local data. And I need to scale it because eventually the effect of the algorithm is to simulate the entire data set. So I kind of augment it by multiplying n here to compensate for missing data effect. And then I still have this noise term at the very end. So essentially what we did are two things. One is to add the consensus term, right? And the other one is to add, replace the centralized data by the local data and then multiply that by n to compensate for the missing data part. So really this has been published in the NeurIPS last year in December. The main result is that actually we just have one single main result, is to show that the convergence of this algorithm in terms of both consensus and also distribution-wise convergence. So this is our algorithm. We have some assumptions. I don't want to go into the technical details here. but they're all in the papers, like Lipschitz continuous assumption, some on the U function here. And then really one of the innovation is to choose this alpha k and beta k as time varying step sizes that goes to 0 given your iteration numbers, and then come up with how you would select alpha 2 and alpha 1 such that we can achieve convergence. So that was one of the innovations in that paper. The final result is fairly simple. One is we achieved the consensus on expectation. So the W tilde K here is the consensus error, so which is Wi minus Wj, and all of them aggregated together, and then we'll get the W tilde K. That will it will converge to 0 in mean square. So this is the expectation result. And the second result is the average. Okay, so W bar is the average among all of the agents. The distribution of the average compared with the target distribution, which is the desired distribution we want to converge to, the KL divergence between them goes to 0. So that means the target, this W bar, the distribution of W bar will converge to the distribution of W, which is our target distribution. And because we have consensus result, so essentially all the agents will converge to the target distribution because they are reaching consensus, and also their average distribution, sorry, the distribution of their average converge to the target distribution. So that's the main theoretical results for the decentralized unadjusted Langevin algorithm. So one of the nice thing about this algorithm is it doesn't have any acceptance criterion. So you can just run it for some time after it converges. You don't have to check whether you want to reject a sample or accept a sample. So next, I want to show you some results. I think I'm good on time. So I want to show you 2 results on the decentralized, like our algorithm. So the first one is a Gaussian mixture. This is a fairly academic example, but we want to see how well the algorithm works. So we start with a prior of theta 1, theta 2. These are 2 scalar parameters with a Gaussian distribution at 0 and with different variances. The first one is 10. The second one is 1. So we're more certain on theta 2. And then we draw this Gaussian mixture. Half of the time we're joined from a Gaussian distribution of with a mean of theta 1 and theta x squared. And half of the time we're joined from theta 1 plus theta 2 and with this sigma x squared as a covariance. So the theta 1, theta 2 is the truths are given by 0 and 1. Okay. So, and then we draw 100 data points, and then we try to estimate what's the distribution of theta 1, theta 2, given the prior and given the data drawn from this Gaussian mixture likelihood. So we draw 100 data points, and then we run our algorithm. We have 5 agents. Each will have 20 data points instead of 100 data points at the central location. Each will have 20 data points, and they talk to each other like a ring topology. So this is the global posterior we kind of estimated based on sampling method, and this would be the ideal posterior. Okay, if we can get, and this is the one we get from the Dula algorithm, so which is our decentralized algorithm. As you can see, there's a kind of a two modes around here. One corresponds to the truth, which is theta 1 equals 0 and theta 2 equals 1. And the other one corresponds to another possibility where your theta 1 is roughly 1 and theta 2 is minus 1. So you can check that that will correspond to a similar possibility. So our samples coming out of this algorithm actually captures kind of this 2 modes behavior fairly well. And also you can see agent 3 and agent 1, they have very similar posterior distribution. That means they reach consensus on their distribution and also on their estimate. So if we were to just use a gradient descent algorithm, we probably will end up with one of the mode instead of capturing the two modes behavior in this specific example. So this is a very simple example just to see if things are working. Then the next one, we kind of move on to a large scale problem where in machine learning, there's a standard data set, which is about images of digital, like handwritten digits. So this is an MNIST data set. And then we train a neural network, LeNet5, and with a uniform prior on their parameters, the weights in the neural network. And we have five agents here. So really the test accuracy after we train after we use the decentralized algorithm is fairly similar, slightly better. I mean, I wouldn't claim it's statistically different, but it's on par with the centralized train algorithm and also the SGD. So then you may ask, okay, why don't we use SGD? The nice thing about this Bayesian learning is it provides you a distribution on parameters. So eventually we can use it to detect out of distribution data. So the SVHN is another set of digit data. Okay, so it's also handwritten digit data. Oh, sorry, it's not handwritten, but it's also digit data. So it's a different distribution from the MNIST. So if we were to use stochastic gradient descent, for the MNIST, we can detect things very well with very high probability. And for the new data set, we detect it with a lower probability, but still it's kind of similar distribution. Whereas if you use the Bayesian learning approach, you will get a completely different distribution. And that based on that distribution, you will detect, okay, I'm getting a different data set than my training data set. So at least you know something additional is happening in your data set. Whereas for SGD, you will always get a number, and then you kind of lose this auto distribution data detection capability offered by Bayesian learning. So to further show that, can see that we're just going to focus on the bottom two diagrams. So this is kind of the diagonal shows, so vertical axis is the actual label and the horizontal axis is the predicted label. So the vertical axis, so on the diagonal, if the data set is MNIST, I get pretty high detection rate. And that's what we want, right? Because we want to detect the correct label from our neural network. But for a different data set, SVHN, what you see here is you got the probabilities are more distributed. You got two modes behavior here that really says, okay, I'm not certain on which one I should choose. So that tells you your data, your input data may be different from the training data distribution, where you actually get a very dominant output from the input data. Whereas for the auto distribution data, you get somewhat kind of distributed between detection of 0 and detection of 8. It allows you to detect something is going on compared to SGD results. So to quickly summarize, we basically just did something to extend the Langevin algorithm to decentralized algorithm. So it's a first order MCMC for Bayesian learning. And also we get some sufficient conditions for the convergence of the algorithm. And also from our results, what we observed is that this decentralized algorithm yield very similar result as a centralized trained model, so which is a very encouraging. We can train the model in a centralized fashion. And also we can provide additional benefit of detecting out of distribution data, which could be helpful when you have security issues in nowadays. Currently, what we're looking at is some other Bayesian learning methods. Particularly, there's a higher order MCMC method based on Hamiltonian dynamics is something we're interested in and we're actually working on. So this basically concludes the first part of the talk. So Joseph, do we take questions now or take it at the end? Sorry, I cannot hear.
Sorry, I muted myself. I would prefer we take it at the end. That way,
sure.
Different time. Okay, thank you.
Yep. Okay. So that was a little bit on the learning side. Now I'd like to move on to a problem we have been looking at for the past couple of years in terms of human-vehicle interaction. This is focused on detect and avoid problems with delayed remote control. So hopefully I mean, my goal here is to describe the problem clearly and then show you some attempt from our side, try to kind of address this problem. Certainly, I welcome your comments and suggestion on kind of whether we're doing the right thing. Okay, so this is the problem. So typically for larger unmanned aircraft system, they're still being controlled from ground control station. Even if they have some automatic functionalities, it still needs to send the surveillance data to the ground control station once it sees the aircraft, and then the ground control station sends the information back, and then this aircraft can maneuver based on that. So because of the communication channel exists, there's always a delay in there. This delay could be between 0.5 to 10 seconds because this actually goes through satellite. So the delay actually, impact ground control station because they have outdated data, right? When you send data in, it's already after 4 seconds. And also the command you received from the ground control station is also delayed. So then it's not actually applicable to your current scenario. So now if we look at this, let's say at t equals 1, I had an aircraft detected, an intruder aircraft. I send it back. There's a delay of 3 seconds. So that means at t equals 4, the pilot sees that. And then the pilot takes some time to respond. So really by t equals 20, okay, the pilot sends command, and then there's another delay of 3 seconds. So by the time you get the command from the first round, it's probably t equals 20 seconds or 23 seconds, you get the data. And that's probably too late if you're really in a very collision imminent scenario where you have some aircraft coming in. So how do we address this issue, right? So really we're facing some decision-making problem here. One is, can the aircraft wait for the command of the ground control pilot? Can they wait? If they don't wait, when they see an intruder, they directly maneuver. Then, I mean, it will be safe, but the human pilot will feel like I'm not controlling the aircraft because the aircraft is maneuvering without my permission. And also, the maneuvers the aircraft produced from its automatic system compared to the pilot maneuvers may be totally different. And the pilot will prefer its own maneuvers because it also involves recovery. So they need to recover to the original path. But if you keep waiting, and then of course, as the intruder coming in, it gets closer and closer, you will have higher risk. So you cannot keep waiting. So there gotta be some kind of gray area where you say, okay, maybe I can wait a little bit, but I after some point I cannot wait. So this is really, how do we decide wait or not wait? And how do we decide how long we can wait? There's obviously a trade-off between safety and the human control experience. And once I receive the pilot command, which is delayed, how do I incorporate that into my current control and maneuver my aircraft according to the pilot suggestion? So really what we're trying to answer is, I have autonomous command coming in here. This is almost real time. And then I have delayed pilot command maybe coming here. What do I do in here to generate one set of command to my flight control system? So what we proposed is sort of a two-step solution to answer the two questions. One is wait or not wait. So we proposed to use a Markov decision process to determine the optimal action at each time, each state, whether you're going to wait or not wait. And then from there, you determine an average waiting time. If your waiting time is passed, then you have to maneuver. You can no longer wait. And then we also developed some sort of optimization that incorporates the pilot command and basically blend it into the maneuver command into the flight control system. So the Markov decision process, I'm sure everybody are familiar with. I'll just try to go over it quickly. This is kind of a cartoon my student created. So I go over that. So this is the intruder, this is the ownership. And then this is intruder. The ownership doesn't want the intruder to enter this big kind of region or the cylinder, which is the collision region. So the intruder has different trajectories. So that's the stochastic part of the intruder model. Also, the on-ship can wait. That means it's going to go straight line. Or it can maneuver. That means it's going to maneuver. So basically, this action, wait, or maneuver plus the intruder stochastic model, motion model, will drive the transition of my state space that consists of the relative state, like position or velocity. And basically, that's going to transition my state space based on the action and the intruder motion model. So then, given that model, what we are trying to optimize this reward, which says if I wait, I'm going to have a positive reward because I have a potential to receive pilot command. But also, I'm going to have some negative reward because potentially this negative reward, it says potentially the aircraft is coming in. I get less distance. So this compensates for that. And then if I maneuver, then there's no reward at all. Sorry, I don't know why this is automatically running. Then the action is to optimize the reward, the accumulated reward over time to get some optimal action at each state, which says I'm going to wait or I'm going to maneuver at each state. And once I have that, I can compute this kind of expected waiting time based on the trajectories that end up into the collision zone. And then I can, for each zone, I can compute their wait time, and then I compute the overall waited time for that particular state. And that would be my waiting time computed for that specific state. Okay, so this is kind of a snapshot of the waiting time at different locations. When you're very far away, you get longer waiting time. When you're very close, like here, this is x direction is almost zero distance, y is zero distance, you get zero waiting time. Okay, so we did some comparison after that. One is we integrate what we proposed. The other one is we have nothing in terms of what we proposed. So really the key difference between the two setup is the one with the integrated system, we have a wait and blend kind of a component, which allows the aircraft to wait for a pilot command, and then once you receive pilot command, it can strengthen that command to avoid maneuver. Whereas this one, it either accepts pilot command or it's going to use its onboard DAA command. There's no waiting and there's no blending of the pilot command. And then we run through different simulations, baselines. These are corresponding to this setup, and different latencies. One is 4, the other one is a Gaussian latencies. So it's a random latency. And the integrated setup corresponds to this one. The latency could be constant, could be varying. And for the IC1, this is the one where I know the latency, so I'm just going to wait for 5 seconds, no matter what. So no matter what the latency, whether I get the data or not, I'm just going to wait for 5 seconds. Whereas the bottom two are going to use the map we created from previous slides to guide me waiting, whether I can wait for 4 seconds or 3 seconds. It's all based on the map. So the result we get is kind of expected for the baseline because there's no waiting. So a lot of DAA overrides occurs, which means DAA gonna take over. It's gonna ignore whatever the humans response and just fly by itself. Whereas in those kind of the integrated setup, it allows the aircraft to wait for a certain amount of time. And so increase the time of, increase the number of commands of waiting or a number of steps of waiting. Also, in terms of number of commands received, the integrated setup also has a much larger amount of command received, almost a 15% increase. That's because of the waiting. Once you start waiting, you can get more command. This is one scenario that kind of shows the difference. We kind of handpicked this scenario just to show the difference. So this is the black line is the intruder trajectory. The green line is the on-ship. So the on-ship going straight, the black line going straight initially. At some point, intruder initiate a turn going this way. If you were used our integrated setup, what you're going to happen is it's going to go straight. It's going to go straight here. And this yellow area is where the aircraft waits. So it waits, okay? And that waiting actually helps. And then the split blue area is when you receive the pilot command, and then strengthen that command to maneuver because the encounter now changes, right? So it strengthens that command to start maneuver. So if you look at the bird eye view, this is basically the intruder ownership go this way, intruder go this way. This is the point where I wait, I strengthen the maneuver, then I avoid the collision like this. Whereas if you do the kind of the standalone or baseline, initially, this is kind of this graph. Initially, you go straight. At this point, the DA, because it sees the potential collision, you directly maneuver the aircraft without considering pilot's preference. And then at this point, you get pilot command. Then the pilot takes over, do something, and then the DA takes over, and then pilot takes over. So it's kind of this unsmooth transition because you're not trying to wait for the pilot command. So obviously, we need to look at the safety. As we talked about, there's a trade-off between safety and pilot experience or the pilot command received. So the baseline setup all have fairly low, sort of the minimum risk of collision, whereas the integrated setup, because of the weighting, they're slightly increased, but in terms of categorizing them, they're still considered like remote likely, unlikely, or remote likely, I think. So so they're still in the same category. And in terms of the number of violations, so this is a probability. This is the number of violations. Actually, we see less number of violations. But what happens is because of waiting for each of a violation, it tends to wait a little bit longer. So it has a kind of a more prolonged a violation of a collision zone. Okay, so that's why this risk is a little bit higher. So, but to quantify that, we actually look at how much increase in terms of another metric. It's called a penetration integral. So this also says they're very low. The one is 0.008. There is roughly about 0.1, 0.01, 0.011. So they're still in the same category. So really, we see here is slight increase in the risk, but a lot more command received, and a lot a very smooth trajectory that could be implemented if we get back the pilot information. So what's the time? Okay, so I can use maybe 1 minute to show some video. So let me jump to let me jump to the last. This is the example I just showed you in the picture. So you can see this one, there's a blending here where this one directly overrides the pilot command. So this is a basic setup, this is an integrated setup. This one blends, so it kind of generates a different trajectory based on the pilot feedback. Whereas this one, just based on DAA, onboard DAA system, it generates something that's not very desired in this situation. So as you can see, this guy maneuvers fairly easily, where this guy has to do a lot of kind of override because it generates something totally different at the beginning. Let me see if I have another one. Yeah, so this is another scenario where this integrated setup allows you to strengthen kind of the pilot command at this point, whereas this one directly execute, which causes a risk because the pilot command is no longer safe. Whereas our system basically strengthens it to kind of generate another small maneuver to deviate from this intruder, which is the gamma in here. Okay. All right. So I'd like to kind of provide some final thoughts. As I said, this is our kind of first shot at the problem. I think it's a very challenging problem to support human in-the-loop, on-the-loop decision-making when there's dynamics. This dynamics for our problem is caused by the intruder's motion, uncertainty in the intruder motion, and also delayed information that's due to communication. So really, the delay hinders the real-time decision-making for pilots, and also, makes the remote control system harder to determine what it needs to do. Okay. And also, I try to tie back to the recent project. Actually, there we have a pilot also involved. Here we have a slightly different dynamic environment. The environment here, the dynamics is actually due to, or uncertainty actually due to the turbulent environment, where the wind has its turbulent components. And also, this ground control station to the pilot will have some communication delays. And also there's workload effect, which we haven't really looked at even for this larger UAV problem. So I think there are a lot of open problems that lies in the human in the loop, on the loop controls, decision making, and how do we better support it in a very challenging scenario such as dynamic and delayed environments. So I'd like to stop it here. I think I don't know. I spent 15 minutes on it. I don't know if it's on time, but
Yeah.
I hope it is. So thank
Yeah.
you very much for your attention.
Thank you very much, Dr. Bai. We were supposed to have 15 minutes for questions, but it's okay. Let me know if anyone has a question. You can either type it in the chat or just unmute yourself and ask the question. So in the meantime, I'm kind of interested in the human in the loop part of your research. That is the second part. Sure. And I'm kind of wondering, so you said it's preliminary. So are you looking at some use cases like having real pilots at the ground control stations? And then, of course, there are issues of workload and how you're going to measure those workloads subjectively or physiologically or whichever ways. These are questions that I have.
Yeah. So that's a very good point. So what all the experiment here we've done, we use a simulated pilot model. So it's actually a simulation model created by MIT Lincoln Lab. So they allows us to simulate different kinds of pilot behaviors. We assume that's kind of how the pilot would respond. But yes, I mean, in the future, we particularly for this, I think for this project, we kind of designed it to support larger UAVs, which is very hard to actually get those pilots. Those are in military. But for this problem, for this small US problem, we're very interested in getting human pilots, whether they are expert or actually novice. We want to get them and actually design the user interface and show them, how measure them according to their I don't know. I mean, you're an expert. Actually, we haven't looked into how to do that experiment very carefully. But yes, we want to do experiment probably for smaller UAVs, not for the larger ones, just because it's hard to get expert or hard to get human subjects.
Okay, I have a couple of research ideas, but of course, as I told you earlier, we'll discuss that later.
Sure, that sounds very interesting. Thank you.
Thank you. Sorry, I have, first of all, I want to thank you for the great presentation. I really enjoyed your talk, and I could relate a lot with the first part of your talk because it's close to what I've been really doing in my research. Let's start actually from the part that you mentioned, the first section of your presentation was a transition from a continuous order equation, the Wiener process, to the centralized scheme. I think it was a slide number 15. Yeah.
Yes.
So
yes.
I know that there are results that show this transition, which is very, very fascinating because area of differential equation and also discrete optimization or discrete let's say methods like the one that you're showing. Each area have been, there are many results in each area, and they could jointly help each other to advance the theory. So yes. One thing I wanted to ask you is that, is the transition or conversion from the continuous process, the Wiener process, to the discrete one, is that an exact approximation, or what's the cost of that transition, first of all?
Yes, okay, that's a very good question. Actually, that touches some differences of our algorithm. So if the alpha k here is a constant step size, then this one will guarantee you convergence. This one will have a bias at the very end due to discretization. What we have found is if we use a diminishing step size, I mean, I guess that's not what we have found, but we were able to show that using diminishing step size, we can asymptotically reduce eventually that bias to zero as k goes to infinity. So that's really the effect of diminishing step size. If you put a constant step size here, there will be a bias in terms of the distribution of this W and your target distribution, they will be quantified in terms of the KL divergence. There's a small bias.
So, okay, yeah, that makes sense. Is the noise that you have added to the outside of the orange box, which seems to be a Gaussian noise?
Yes.
Is that a consequence of this discretization, or it's part of?
No, well, so the Wiener process, once you discretize it, it becomes a Gaussian process, Gaussian noise. Yeah. So that part is exact.
Interesting.
Yeah, this part is so yeah, this part is not. And also that what's interesting is they are scaled differently. So the alpha k and this one is the square root of alpha k. So if alpha k is small, this one is actually could be large. So eventually there's a balance between, you know, the exploitation. If you're very far from your like zero gradient part, this one will dominant. But if you're close to zero gradient part, this one will dominant, because this guy will, yeah. So you're gonna explore more once you reach the zero gradient part. Yeah.
Right. It's interesting. You know, recently I've read papers that use the idea of increasing sample size throughout their scheme, and they vanish. They basically make that noise, the Gaussian noise that you have there, fade away. I have a feeling that if, based on my understanding, you're using one data at a time, I feel like if at each iteration of your algorithm, at each time k, more and more samples are taken in an increasing fashion, that might lead to an acceleration of your scheme, which intuitively, you know, would make sense. But of course, there's a cost of taking more samples. But in terms of the theoretical speed of, you know, convergence, it actually would help. So that's one comment I had. The other is, well, let me ask you this question. This UI function that you have,
right,
which reminds me of, you know, the gradient of UI basically is like a gradient in SGD.
Yeah.
This looks like a convex function to me. Is that true?
No. So not necessarily. It can be a convex. So this relates to this guy. So so the assumption we have is the target distribution have this LSI. This is actually mimics the PL condition optimization. So we can talk about that. But really, the UI can be convex, in which case it's going to result in log concave measures, which means P star W will be log concave, because it's e to the minus UI, right? So it's when you take the log, it becomes concave. So that's one, but we can have others. You can have like this, we can take this one. This black line is definitely, it's a distribution, but it's definitely not log concave. Whereas the dashed line is log concave, it's a Gaussian, so it's a log concave. So you can deviate from a convex function in terms of UI, but you have to satisfy this condition. And another example is if you are non-convex within a fixed region and then convex, strongly convex outside that region, then it's also satisfied this this condition. So there are examples showing kind of this is a generalization of convex.
Interesting. So do you mean that in the mean sense, in the expectation sense, would that
so this equation is, you can think about this as expectation. So this is, yeah, this is any function g log g in terms of the target distribution, and this side is also that.
So you're saying even that integral could be non-convex. Is that what you're saying?
Yeah, well, that integral is, yeah, any smooth function. So this is a pretty strong condition. You need any smooth function g, non-convex, convex, whatever. So any smooth function g for the given desired posterior, it must satisfy this. So it's a property of the PW star. Yeah.
I look more into it. I was looking at your paper, the Neurips paper, and so I was trying to look into the details. That was very interesting. So I don't want to take more time, but I also wanted to mention that, so it looks like you're, in the comparisons, you're comparing the idea of decentralized Bayesian learning with SGD. Right. So when you're saying SGD, do you mean, so what is the gradient there? So what function, is that the same, is that an optimization problem that you're
you can, I think I apologize, I wasn't being rigorous on that comparison. I think really what we're comparing is based on, where's my, formulation. Sorry, it should be this. So based on this one, right, you can say I can, instead of getting the posterior, you can say I want to get a maximum likelihood estimate. So that would be an estimate maximizing the likelihood. So that would be a single estimate. And then that would be your, you can take gradient of that function and drive that to 0, then you'll get a one single estimate. Or you can do maximum a posterior estimate, which means you maximize the entire thing, but you still get a single estimate.
I see.
Yeah.
Yeah. So definitely, I'll be very, happy to talk to you about some ideas, because I know that, for example, the idea of gradient tracking, which has been recently, trending topic in this area of decentralized optimization.
Yes.
I feel like it actually might work within this area of Bayesian learning. And if that's the case, then actually it would be an acceleration of your scheme. So I would be really happy to talk to you after your presentation, and I'll email you.
Oh,
But
definitely. Yeah, I look forward. I think we should have some collaboration ideas, definitely. Yeah. Yeah, thank you very
so
much.
Yeah.
For the questions and comments.
Okay, so thank you. Are there any other questions? I suppose it's already 3:30. You have Dr. Bai's email. You could shoot him an email so that the conversations can continue. But in the meantime, join me. Thank Dr. Bai.
Joseph, just one quick comment. First of all, thank you for organizing this seminar and good talk. And sorry, I had to jump in and out. I couldn't be here for the whole presentation. But it looks like something, Dr. Bai, that this is something that is very relevant to what Farzad does, but also Bing Yao and others in our department. So I would encourage, collaboration between. I see Imran was there a little bit. Well, he's still here, but the faculty in mechanical and industrial, I think we have quite a bit in common. So I would encourage you to collaborate and work on proposals, because there's a lot of complementary or maybe even overlapping interests. And so together, I think you guys can rock. So thank you for a great presentation. And thank you, Joseph, for starting off our very first seminar this time around with the bang.
Yeah, thank you, Sundaresh, and thank you all for being part of this very first seminar series. I mean, the weather had not been so generous, but you took time to be present to listen to Dr. Bai for this very insightful presentation. We have a lot more coming this semester, and I hope you can attend these seminars as we announce them. Thank you and have a very good rest of your day. Okay, bye-bye.
Thank you, Joseph, for the opportunity. Thank you, everyone, for your attention. Thanks.